Our galaxy has 100 billion stars. Even if only a tiny fraction had life, there should be thousands of civilizations. So why is the universe silent? Every science fiction empire gets one thing spectacularly wrong. Every movie, every novel, every galactic federation. They all assume the same idea. That if a civilization becomes advanced enough, it will eventually spread across the entire galaxy, star by star, system by system, until the Milky Way becomes one enormous interconnected civilization. But here's the uncomfortable truth. According to the actual laws of physics, that future may be impossible. Not difficult, not unlikely, impossible. Because the universe is not built to allow coherent control across distances this vast. Distance fights you, time fights you, energy fights you, and entropy quietly dismantles everything you build. If you really run the numbers, the galaxy begins to look less like a frontier and more like a giant machine designed to keep civilizations isolated from one another. And tonight, we're going to explore why. But before we begin, a quick favor. If you enjoy these deep dives into the strange physics that shapes our universe, take a moment to like the video and subscribe to the channel. It genuinely helps more people discover this kind of science storytelling, and it keeps these long explorations possible. Now, get comfortable, dim the lights, and let's take a journey into the real scale of our galaxy. Most people imagine the Milky Way the same way. A neat spiral. A flat cosmic pinwheel with graceful arms of stars wrapping around a bright center. You've probably seen it on posters in classrooms, or glowing on astronomy websites. It looks organized, elegant, almost manageable. But that image is deeply misleading. The real Milky Way is not a flat drawing. It is a three-dimensional monster. From one edge of the visible disk to the other, the galaxy stretches roughly 100,000 light-years across. To understand what that means, we need to pause for a moment and talk about light. Light moves incredibly fast. Almost 300,000 kilometers per second. Fast enough to circle Earth more than 7 times in a single second. Yet even at that speed, a beam of light needs 100,000 years just to cross our galaxy. That means if a signal left one side of the Milky Way when modern humans first began building cities, it still wouldn't have arrived yet. And that's just the diameter. The galaxy also has thickness. In the outer spiral arms, the disk is about 2,000 light-years thick. Near the center, the galaxy bulges upward and downward to nearly 12,000 light-years. And beyond that visible disk lies something even larger. A vast spherical halo of dark matter, ancient star clusters, and scattered relic stars extending more than 200,000 light-years in diameter. In other words, the Milky Way is not a flat spiral. It's a colossal three-dimensional ocean of stars, and most of that ocean is empty. Terrifyingly empty. Here's another number that sounds simple, until you really think about it. Our galaxy contains somewhere between 100 billion and 400 billion stars. Even astronomers can't narrow that estimate down precisely. That uncertainty alone tells you something remarkable. We don't even know how many stars exist in our own galaxy. Dust clouds in the galactic plane block huge regions of space from optical telescopes. Entire stellar populations hide behind curtains of gas and debris. Infrared and radio telescopes have revealed enormous numbers of stars that visible light surveys completely missed. Even after more than a century of modern astronomy, we're still cataloging the basic contents of our own galactic neighborhood. Now imagine trying to explore it. Let's try a simple thought experiment. Suppose you decided to count every star in the Milky Way, one per second. No sleeping, no eating, no breaks, just counting. At that pace, reaching 100 billion stars would take more than 3,000 years. Counting the upper estimate of 400 billion would take around 12,700 years, longer than all of recorded human civilization. and each of those stars sits inside its own vast bubble of space, separated from its neighbors not by miles, not by millions of miles, but by light years. In our region of the galaxy, the solar neighborhood, the typical distance between stars is roughly 4 to 5 light years. 1 light year equals about 5.88 trillion miles. So the average gap between neighboring stars around us is about 24 trillion miles. Try to picture that for a moment. This isn't like traveling between cities. It isn't even like crossing an ocean between continents. It's more like trying to cross a desert so large that the next oasis is literally trillions of miles away. And nothing built by humans has ever come remotely close to crossing such a distance. Take Voyager 1, the most distant human-made object ever launched. It has been traveling through space for more than 45 years. During that time, it has covered roughly 15 billion miles. That sounds impressive, until you compare it to interstellar space. At its current speed, Voyager would need over 70,000 years to reach the nearest star system, Alpha Centauri, just 4.24 light years away. And that is the closest star to our sun. Every other destination is farther, sometimes vastly farther. But here's where things become even more interesting. The galaxy is not evenly filled with stars. Some regions are crowded, others are nearly empty. Near the center of the Milky Way lies the Galactic bulge, where stars pack together so densely that the night sky from a nearby planet would blaze with thousands of suns, but travel outward to the edges of the galaxy, and the gaps between stars can stretch to 10, 20, even 30 light years. Leave the disk entirely and enter the halo. And individual stars may drift hundreds of light years apart. Imagine trying to build a civilization across terrain like that. Some regions overflowing with stars, other regions almost completely empty. Expansion would not spread smoothly like ink in water. It would stumble through a chaotic landscape of crowded clusters and enormous voids, every step outward becoming harder than the last. And this leads to a critical realization. When people talk about spreading across the galaxy, they usually imagine it as a simple chain reaction. Reach one star, then the next, until eventually the whole galaxy is settled. But that assumption hides a crucial mistake, because not all forms of interstellar activity are the same. In fact, there are 3 completely different levels of expansion: exploration, settlement, and empire. And confusing those 3 ideas is where almost every discussion about galactic civilization goes wrong. In the next part of this journey, we'll examine those 3 stages, and we'll discover why reaching another star might be possible, while building a true galactic civilization may collide with something far more powerful than engineering: the fundamental laws of the universe itself. A civilization reaching another star sounds like the beginning of a galactic empire. But in reality, it might only be the first step of a very long and very lonely journey. Because when scientists talk about spreading through the galaxy, they're usually describing 3 completely different things: exploration, settlement, and empire. They sound similar, but the physics behind them is wildly different. And confusing these stages is one of the biggest reasons people underestimate how difficult a true galactic civilization would be. Let's start with the simplest one: exploration. Exploration is exactly what it sounds like. Sending probes, robotic scouts, scientific instruments, maybe tiny autonomous spacecraft, machines that leave their home star system, travel through interstellar space, collect data, and send information back. From a physics standpoint, this is actually the most achievable form of interstellar activity. In fact, humanity has already started doing it. Voyager 1 and Voyager 2 are currently traveling through interstellar space right now. They were launched in the 1970s, originally designed to explore the outer planets of our solar system. But after completing their mission, they just kept going. Today, Voyager 1 is more than 24 billion kilometers from Earth, still drifting outward into the galaxy, still sending faint radio signals back to us across unimaginable distances. And yet, even this incredible achievement reveals the brutal reality of interstellar travel. Voyager isn't headed toward any star. Not really. At its current trajectory and speed, it will pass near another star system in about 40,000 years. By then, Earth itself may be unrecognizable. Languages will have changed. Continents may have shifted. Civilizations may have risen and fallen dozens of times. Exploration, in other words, can reach across stars. But it does so painfully slowly. And that leads to the next stage. Settlement. Settlement is an entirely different challenge. Exploration sends machines. Settlement sends life, people, ecosystems, entire living environments that must survive for decades, centuries, or even millennia. Imagine building a spacecraft that could carry thousands of people to another star. The ship would need food production, water recycling, radiation shielding, artificial gravity, medical facilities, education, governance, culture. In other words, a tiny, self-contained world. And that world would have to survive the harshest environment imaginable. Deep interstellar space, where temperatures hover just a few degrees above absolute zero, where cosmic radiation constantly bombards unshielded structures, where even a grain of dust hitting the ship at high velocity could release the energy of an explosion. Interstellar space may look empty, but it is not safe. Now imagine that journey lasting hundreds of years. Generations would live and die aboard the ship before it ever reached its destination. Children would be born who had never seen the home world. Entire cultures would evolve inside a spacecraft. By the time the ship arrived, the settlers might no longer feel connected to the civilization that launched them. And this leads to a fascinating question. If a generation ship left Earth today and arrived at another star 300 years from now, would those descendants still consider themselves human in the same cultural sense? Or would they have become something new, something shaped entirely by life in transit? Interstellar settlement isn't just an engineering problem, it's a sociological one, a psychological one, a biological one. But even if we solved all those challenges, even if humanity successfully built thousands of generation ships, even if we colonized star after star across the galaxy, there is still one final stage. And it is the hardest of all, empire. Empire is not just spreading to other stars, it means coordinating them. A true galactic civilization would require communication, trade, governance, and cooperation between star systems separated by light years. And that's where the universe starts saying, no. Because information cannot travel faster than light. That's not a technological limitation. It's a law of physics. No signal, no spacecraft, no message, no command, no idea can move faster than light through space, which means the moment a civilization expands across multiple star systems, it automatically becomes fragmented. Let's imagine two colonies, one around Earth, one around a star 20 light years away. If the Earth government sent a message to that colony today, it wouldn't arrive for 20 years. And the reply would take another 20 years to come back. A single conversation would require 40 years. Now imagine trying to run a government like that, passing laws, managing crises, coordinating defense, handling trade disputes, every decision delayed by decades, every misunderstanding stretched across generations. At that point, it's no longer one civilization. It's a loose collection of independent worlds. And the problem gets worse the farther expansion goes. At 100 light years, communication delays reach centuries. At 10,000 light years, messages require 10,000 years to arrive. Entire civilizations could rise and collapse before the first reply comes back. And this creates a strange paradox. The larger a civilization grows, the less connected it becomes. Expansion destroys unity. The galaxy may allow exploration. It may even allow settlement. But empire? Empire collides directly with the speed of light. And the speed of light is not negotiable. But there's an even deeper twist. Because distance isn't the only thing working against galactic civilizations. Time itself becomes a powerful enemy. Stars move. Orbits shift. Galaxies evolve. The Milky Way is not a static map of fixed points in space. It's a swirling, rotating system. Our Sun, for example, is currently orbiting the center of the galaxy at about 220 kilometers per second. At that speed, it takes roughly 225 million years to complete a single orbit around the Milky Way. 1 galactic year, which means that during the lifetime of a civilization, entire star systems slowly drift across the galaxy like boats in a cosmic ocean. The neighbors you start with may not be the neighbors you end with. And over millions of years, the structure of the galaxy itself changes. Star clusters disperse. New stars are born. Old stars die. Regions of the galaxy become hostile or quiet depending on waves of supernova explosions. In other words, even the map of the galaxy is temporary, which raises a haunting possibility. Maybe the reason we don't see enormous galactic empires is not because intelligent life is rare. Maybe it's because the universe itself makes those empires impossible to maintain, not through war, not through catastrophe, but through something far more subtle: distance, time, and the unbreakable speed limit of reality. But the most surprising obstacle of all is still ahead. Because even if a civilization somehow solved travel, communication, and settlement, there is another force waiting in the background. A quiet law of nature that slowly dismantles every structure in the universe. A law that eventually affects stars, planets, civilizations, and even galaxies. Entropy. And once entropy enters the story, the dream of a galactic empire becomes even stranger than science fiction imagined. That's where our journey continues next. There is a quiet law of nature that governs everything in the universe. It doesn't make headlines. It doesn't explode like a supernova. It doesn't bend space like a black hole. Yet over time, it defeats every structure that has ever existed. Stars, planets, machines, civilizations, even galaxies themselves. This law is called entropy. And once you understand it, the dream of a galaxy-spanning civilization starts to look very different. Entropy is often described in a simple way. Things tend to move from order to disorder. A neatly stacked tower of blocks eventually falls. A hot cup of coffee cools down. A clean room slowly becomes messy if nobody maintains it. Energy spreads out. Structures decay. Systems drift toward randomness. But entropy is not just about messiness. It is about energy becoming harder to use. That detail is crucial, because civilizations survive by using energy. Every city on Earth runs on energy flows. Electricity through wires, fuel through engines, food through ecosystems. The moment those flows stop, the civilization collapses. Now imagine stretching that system across light years, across hundreds or thousands of star systems. Maintaining a galactic civilization would require enormous amounts of energy just to keep everything connected. Communication networks, transport systems, data infrastructure, manufacturing, maintenance, defense. And the farther those systems spread, the more energy they require, which leads to a strange cosmic reality. The larger a civilization becomes, the more fragile it also becomes, because its survival depends on ever-growing energy consumption. To understand this problem better, imagine trying to heat a house. When the house is small, it's easy. A single heater keeps the rooms warm. But if the house suddenly expands into a giant mansion, then into a stadium, then into an entire city. The same heater becomes useless. You need more power, more infrastructure, more fuel. Civilizations behave the same way. As they grow, their energy demands grow faster than their size. Economists call this complexity cost. Every new layer of organization requires more resources just to maintain stability. More administrators, more communication, more coordination, more energy. Eventually, systems reach a tipping point where maintaining complexity becomes harder than expanding it. History is full of examples. The Roman Empire expanded across Europe, North Africa, and the Middle East. But the larger it became, the harder it was to govern. Communication delays slowed decisions. Supply chains stretched thin. Frontiers became difficult to defend. And eventually, the cost of maintaining the empire exceeded the benefits. It fragmented. Not because people forgot how to build roads or cities, but because complexity itself became too expensive. Now imagine that same problem, but scaled to the size of a galaxy. Entropy introduces another subtle challenge: maintenance. Every machine wears out. Every structure degrades. Even the most advanced spacecraft would require constant repair. Radiation damage, micrometeorite impacts, material fatigue. Over thousands of years, those small failures accumulate. Keeping a single space station operational is already an enormous challenge. The International Space Station requires constant maintenance from astronauts and ground control. Without human intervention, it would eventually become unusable. Now imagine maintaining millions of structures across thousands of star systems. Even highly advanced automation would struggle to keep up with that scale, because entropy never stops. Not for a moment. Every second, systems are degrading somewhere. Every second, something needs repair. And the farther those systems spread across space, the harder it becomes to fix problems quickly. But entropy affects something else as well: information. Civilizations depend on knowledge, science, engineering, history, culture. But information can also decay. Data storage systems fail. Languages evolve, archives are lost. Libraries burn. We often imagine advanced civilizations as permanently stable. But history tells a different story. Knowledge can disappear surprisingly fast. During the collapse of ancient civilizations, entire technological capabilities vanished. Concrete formulas used by the Romans were forgotten for centuries. Astronomical knowledge recorded by ancient cultures disappeared when their societies collapsed. And those were relatively small civilizations. Now imagine knowledge stored across thousands of star systems, separated by decades or centuries of communication delay. Each colony evolving independently, each adapting to its own environment. Over time, their cultures would diverge, their languages would shift, their technologies might develop along completely different paths. After a few thousand years, those colonies might no longer recognize each other as the same civilization. They would become something more like distant relatives, connected by ancient history, but no longer unified. And then there is the final effect of entropy: time. Because the universe itself is slowly moving toward a colder, more diluted state. Stars burn their nuclear fuel. Galaxies slowly exhaust their gas reserves. Star formation gradually declines. Billions of years from now, the universe will contain fewer new stars. Energy sources will become rarer. Civilizations that depend on stellar energy will eventually face a long-term resource challenge. In other words, even if a civilization survives technological challenges, even if it spreads across thousands of star systems, even if it maintains communication networks for millions of years, the cosmic environment itself will slowly become less hospitable. Entropy always wins in the end. Not dramatically, but inevitably. This realization leads to a fascinating possibility. Perhaps the most advanced civilizations in the universe do not expand endlessly. Perhaps they do something else. Perhaps they optimize instead of expanding. Rather than spreading thin across vast regions of space, they may concentrate around stable energy sources, dense clusters of infrastructure, efficient systems designed to minimize entropy losses. Instead of a sprawling empire, they might resemble something more like a perfectly engineered city, compact, highly efficient, carefully balanced with the energy resources available. This idea leads to one of the strangest possibilities in astrophysics, a possibility that might explain why the universe appears so quiet. Maybe advanced civilizations are not spreading across galaxies. Maybe they are becoming harder to detect, smaller, more efficient, more focused inward than outward. And if that's true, then the silence of the cosmos may not mean we are alone. It might mean the most advanced civilizations learned something we haven't yet, that the path to survival in the universe is not endless expansion, but mastering the delicate balance between energy, complexity, and entropy. And in the next part of our journey, we'll explore an even deeper mystery. Because if civilizations really do tend to fragment, collapse, or hide, then a haunting question emerges. Where is everyone? Why does the Milky Way look so quiet, when the physics of life suggests the galaxy should be full of it? In 1950, a physicist named Enrico Fermi asked a question that still echoes through astronomy today. It was a simple question, almost casual, but it carried enormous implications. During a lunchtime conversation with colleagues, Fermi suddenly asked, "Where is everybody?" He wasn't talking about people. He was talking about aliens. Because when you actually run the numbers about life in the universe, something strange appears. Our galaxy is incredibly old. The Milky Way formed more than 13 billion years ago. Our sun, by comparison, is relatively young, about 4.6 billion years old. That means there were billions of years before Earth even existed, when other star systems could have formed planets that might have developed life, and possibly intelligent civilizations. Now imagine a civilization that developed just 1 million years before humanity. 1 million years sounds enormous to us, but on a galactic timescale, it's practically nothing. The Milky Way has existed for 13,000 million years. 1 million years is less than 1/10,000th of that time. If such a civilization existed, and if it expanded slowly, even cautiously, across space, it could theoretically spread across the entire galaxy in a surprisingly short time. Astronomers have modeled this scenario many times, even with relatively slow spacecraft traveling a fraction of the speed of light. A wave of exploration and colonization could spread from star to star, each new colony eventually launching its own missions outward, a branching expansion, like seeds carried by the wind. Over time, that wave would ripple across the Milky Way. Simulation suggests something remarkable. Even conservative estimates show that a civilization could explore the entire galaxy in 10 million to 100 million years. That might sound like a long time, but remember the age of the galaxy. Compared to 13 billion years, that expansion time is tiny. It means that if even one technological civilization appeared early in the Milky Way's history, there's been more than enough time for it to spread everywhere, every star system, every corner of the galaxy, including ours. And yet, when we look up at the sky, we see nothing. No alien spacecraft, no megastructures surrounding stars, no clear signals from advanced civilizations. Just silence. That contradiction is what scientists call the Fermi Paradox. The universe should be full of life, but the sky looks empty. To understand why this is puzzling, imagine a simpler scenario. Suppose you walk into a forest. You see trees, rivers, animals. Everything looks normal. But then you notice something strange. There are no birds. Not a single one. No chirping, no wings, no nests. Just quiet. At first you might think you simply haven't seen one yet. But the longer you explore, the stranger it becomes. Birds should be everywhere in a healthy forest. Their absence would raise a disturbing question. What happened to them? The Milky Way is that forest. And intelligent civilizations are the birds we expected to hear. Scientists have proposed many possible answers to the Fermi Paradox. Some are optimistic, some are unsettling, and some are downright terrifying. Let's start with the simplest explanation. Maybe intelligent life is extremely rare. Life itself might be common. Simple organisms could exist on countless planets. But evolving intelligence capable of building technology might require an extraordinary chain of unlikely events. On Earth, life appeared relatively quickly after the planet formed. But complex multicellular life took billions of years to evolve. And technological intelligence appeared only once. Humans. It's possible that intelligent species are incredibly rare cosmic accidents. If that's true, we might simply be the first, or among the very few. Another possibility is that civilizations don't last very long. Technological societies might tend to destroy themselves. War. Environmental collapse. Uncontrolled artificial intelligence. Runaway biotechnology. Energy crises. History on Earth shows how fragile, complex societies can be. Our entire technological civilization has existed for only a few hundred years. That's barely a blink of an eye compared to cosmic timescales. If most civilizations collapse soon after developing advanced technology, then the galaxy might be filled with the ruins of extinct cultures, planets that once hosted intelligent life, but are now silent. There is also a more unsettling possibility. Maybe advanced civilizations deliberately avoid being visible. Broadcasting your presence into the galaxy might be dangerous. After all, we have no idea who or what might be listening. Some scientists call this idea the dark forest hypothesis. The concept is simple. Imagine the galaxy as a dark forest at night. Every civilization is a hunter moving silently between the trees. No one announces their location. Because revealing yourself could attract predators. If even one aggressive civilization existed, the safest strategy for everyone else would be silence. Hide, stay quiet, avoid attention. In that scenario, the universe might actually be full of life, but every civilization is deliberately invisible. There is another explanation that feels almost philosophical. Perhaps we are looking for the wrong things. When people imagine advanced civilizations, they usually picture something similar to us. Bigger cities, more powerful technology, larger spacecraft. But truly advanced intelligence might evolve in completely different directions. Civilizations millions of years older than humanity could become unrecognizable. They might abandon physical expansion entirely. They might exist inside vast digital environments, artificial worlds running on ultra-efficient computing systems. From the outside, such civilizations might produce almost no detectable signals. They could be living their entire existence inside compact technological habitats, invisible to distant observers like us. But here's the most fascinating twist of all. The Fermi Paradox may not just be about aliens. It might actually be about our future. Because every explanation for the silence of the galaxy raises the same question. What happens to technological civilizations over long periods of time? Do they expand, collapse, hide, transform into something entirely new? Right now, humanity is standing at the very beginning of that story. We are the first species on Earth to develop radio communication, space flight, artificial intelligence, planetary scale industry. And we've had these technologies for barely a century. From a cosmic perspective, we are newborns. The decisions our civilization makes in the coming centuries could determine which path we follow. Expansion, self-destruction, transformation, or something we can't even imagine yet. And in the next part of our journey, we'll explore one of the most extraordinary ideas scientists have ever proposed. A concept that suggests advanced civilizations might leave enormous fingerprints on the universe itself. Not through spacecraft, not through radio signals, but through gigantic engineering projects built on the scale of entire stars. Imagine a civilization so advanced that planets are no longer enough. Their cities no longer sit on continents. Their industries no longer depend on fossil fuels, solar panels, or nuclear reactors. Instead, they harvest the energy of entire stars. Not metaphorically, literally. This idea might sound like science fiction, but it was actually proposed by a real physicist in the 1960s. His name was Freeman Dyson, and he suggested something astonishing. If a civilization becomes advanced enough, it might eventually try to capture all the energy produced by its star. Not just a tiny fraction of sunlight like we do on Earth, but the entire output. Every photon, every watt, every second. To understand why, we need to talk about energy again, because energy is the ultimate currency of civilization. The more energy a society can harness, the more work it can do. More computation, more transportation, more manufacturing, more knowledge. On Earth today, humanity uses roughly 18 terawatts of power. That's 18 trillion watts. It sounds enormous. But compared to the sun, it's almost nothing. The sun produces about 380 septillion watts of energy. That's a 3 followed by 26 zeros. Every second. Earth intercepts only a tiny slice of that power. Less than 1/billionth of the sun's total output. The rest radiates into space, completely unused. From a purely engineering perspective, that's an incredible waste. And an advanced civilization might look at that unused energy and think, why let it escape? Freeman Dyson proposed a radical solution. Instead of building energy collectors on a planet, build them around the entire star. A gigantic swarm of satellites. Solar collectors orbiting in every direction. Together they would capture most of the star's radiation and convert it into usable energy. This structure became known as a Dyson sphere, although the name is a little misleading. Dyson himself didn't imagine a solid shell around a star. That would require impossible amounts of material. Instead, he imagined something more practical. A Dyson swarm. Millions, or even billions, of orbiting structures, each collecting a portion of the star's energy, working together as a vast stellar power plant. If such a system existed around our sun, the available energy would be staggering. A fully developed Dyson swarm could capture hundreds of trillions of times more power than humanity currently uses. Enough to support civilizations far beyond anything we can imagine today. Massive computation networks, interstellar manufacturing, gigantic habitats containing trillions of inhabitants, entire artificial ecosystems floating in space. In many ways, building structures around stars might be easier than colonizing planets, because space offers something planets do not: room. No gravity wells, no atmosphere, no weather. Just open space where enormous structures can be assembled piece by piece. In fact, some scientists think that long-term space civilizations might prefer orbital habitats instead of planets. A rotating habitat can create artificial gravity. Temperature can be precisely controlled. Day and night cycles can be engineered. Agriculture can be optimized. From an engineering perspective, space habitats could eventually become more comfortable than natural planets. But Dyson's idea led to another fascinating thought. If advanced civilizations really do build stellar megastructures, we might be able to detect them. Not by seeing the structures directly, but by observing their waste heat. Remember entropy. No energy system is perfectly efficient. Any civilization capturing stellar power would inevitably produce heat, and that heat would radiate into space, mostly as infrared radiation. So astronomers began asking an interesting question. What if we look for stars that appear unusually dim in visible light, but glow brightly in infrared? That combination might suggest that something is absorbing the star's energy and re-emitting it as heat. In other words, the signature of a Dyson swarm. In the past few decades, scientists have actually started searching for such signals. Large infrared sky surveys have scanned millions of stars, looking for anomalies, objects that don't behave like normal stellar systems. And occasionally, they find something strange. One of the most famous examples appeared in 2015. A star known as KIC 8462852, better known as Tabby's star. Astronomers noticed that this star behaved in an extremely unusual way. Its brightness dropped dramatically, not by a few percent, but sometimes by 20% or more. And these dips didn't follow a predictable pattern. Planets orbiting a star can block some light during transit, but those events are regular and symmetrical. Tabby's star was different. The dimming was chaotic, irregular, sometimes lasting days, sometimes weeks. At first, astronomers struggled to explain it. Dust clouds, comet swarms, instrument errors. None of the explanations perfectly matched the data, and naturally, some people began asking a provocative question. Could this be evidence of a massive artificial structure orbiting the star? A Dyson swarm under construction? Now, to be clear, most scientists believe the Tabby star mystery likely has natural explanations. Large clouds of dust or debris, possibly the remnants of planetary collisions. But the event revealed something important. For the first time in history, humanity had reached a point where we could seriously discuss detecting alien megastructures. Not through speculation, but through astronomical data. In other words, the search for extraterrestrial intelligence had entered a new phase. Instead of listening only for radio signals, we could search for astroengineering, gigantic technological fingerprints written across the stars. And this leads to a fascinating possibility. If civilizations tend to become more efficient over time, as we discussed earlier with entropy, then large-scale energy harvesting might be a natural evolutionary step. Young civilizations burn fuel. Developing civilizations build planetary infrastructure. Mature civilizations might eventually surround their stars with energy collectors. From that perspective, Dyson swarms might represent a common stage in the life cycle of technological societies. If that's true, then somewhere in the Milky Way, there could already be stars wrapped in vast networks of machines, silent, invisible to the naked eye, but glowing softly in infrared light, waiting for us to notice. And yet, even with modern telescopes scanning millions of stars, we still haven't found clear evidence of such megastructures, which raises another question. Maybe Dyson swarms are not the final stage of civilization. Maybe truly advanced societies go even further. Instead of capturing energy from a single star, they might learn to manipulate the energy of entire galaxies. And if that sounds impossible, the next idea we'll explore might change the way you think about the limits of technology forever. Capturing the energy of a single star would already place a civilization far beyond anything humanity has achieved. But in the 1960s, a Soviet astrophysicist named Nikolai Kardashev asked an even bigger question. What if we could classify civilizations, not by their culture, not by their technology, but by the amount of energy they control? Energy, after all, is the ultimate measure of capability. Every technological achievement ultimately comes down to energy use. The engines we build, the computers we run, the cities we power. All of it is energy transformed into useful work. So Kardashev proposed a simple but powerful scale, 3 levels of civilization, each defined by a massive leap in energy control. A Type 1. Civilization controls the energy resources of an entire planet. That includes solar power, wind, oceans, geothermal energy, and potentially fusion. Essentially, everything the planet naturally provides. To reach this level, a civilization would need access to around 10 to the power of 16 to 10 to the power of 17 watts of power. Humanity is not there yet. Right now we operate at about 10 to the power of 13 watts, which means we are still a fraction of a Type 1 civilization. Some scientists estimate we might reach this level in a few hundred years, if our technological growth continues. But even Type 1 is only the beginning. A Type 2 civilization controls the energy of an entire star. This is where Dyson swarms enter the picture. Harnessing the output of a star like the Sun would provide about 10 to the power of 26 watts of power. 10 billion times more energy than a Type 1 civilization. With that kind of power, the limits of technology start to shift dramatically. Entire planets could be engineered, asteroids reshaped into habitats, artificial worlds constructed in orbit, computational systems capable of simulating entire civilizations. A Type 2 society might spread throughout its star system, building infrastructure around planets, moons, and asteroid belts. To observers like us, their solar system might look more like an industrial ecosystem than a natural one. And then comes the most staggering level of all, a Type 3 civilization. Instead of controlling a single star, it harnesses the energy of an entire galaxy. That means billions of stars. The combined power output could reach around 10 to the power of 36 watts. To put that into perspective, a Type 3 civilization would command roughly 10 billion Dyson spheres worth of energy. At that scale, the distinction between astronomy and engineering begins to blur. Stars themselves might become components in a vast technological network. Entire stellar systems could be repositioned. Galactic-scale infrastructure might guide the flow of energy across thousands of light years. If such a civilization existed in the Milky Way, it would likely leave enormous observable fingerprints. Regions of the galaxy where stars appear dimmer than expected or emit unusual patterns of infrared radiation. Astronomers have actually searched for signs of this. So far, they have found none. But the Kardashev scale has an interesting twist. It's not necessarily about bigger empires. It's about better energy control. A civilization could theoretically reach very high energy efficiency without spreading across vast areas of space. For example, a society might concentrate its infrastructure around a small number of stars, while using extremely advanced technology to extract energy with almost perfect efficiency. In that case, it might achieve Type 2 or even Type 3 energy levels, without leaving obvious megastructures everywhere. This idea has led some scientists to propose a fascinating concept. Perhaps advanced civilizations don't expand outward endlessly. Perhaps they become incredibly efficient inward systems. Imagine a civilization that compresses enormous computing power into compact structures, using minimal energy loss, minimal waste heat, minimal detectable emissions. From the outside, such a civilization might be almost invisible. There's another possibility that pushes the imagination even further. Some physicists speculate about Type 4 civilizations. This isn't part of Kardashev's original scale, but the idea naturally extends from it. A Type 4 civilization would control the energy of an entire universe, not just stars, not just galaxies, but the total energy content of cosmic space itself. At this level, civilizations might manipulate black holes, control dark matter, or even engineer new universes through exotic physics. These ideas remain speculative, but they highlight something fascinating. Once a civilization begins mastering energy at large scales, its technological possibilities expand far beyond anything we currently understand. But here's where the story becomes even more interesting, because the Kardashev scale assumes something important: that civilizations continue growing indefinitely, more energy, more infrastructure, more expansion. But as we discussed earlier, entropy and complexity might push civilizations in a different direction. Instead of growing larger, they might become more efficient, smaller, more compact, more optimized. Think about how technology on Earth has evolved. Early computers filled entire rooms. Now smartphones contain far more computing power. Inside devices small enough to fit in your pocket. Over time, technology tends to shrink, become more efficient, consume less energy per task. If that trend continues for millions of years, advanced civilizations might not look like sprawling galactic empires. They might resemble hyper-efficient technological ecosystems, compact clusters of infrastructure orbiting stars, or even microscopic computational systems operating near the limits of physics. This leads to a fascinating reinterpretation of the Fermi Paradox. Maybe we don't see Type 3 civilizations, because the most advanced societies don't leave enormous structures everywhere. Instead, they might concentrate their activities into extremely dense technological environments. Efficient, quiet, difficult to detect across interstellar distances. In other words, they might deliberately minimize their cosmic footprint. And this raises a subtle but profound question. If advanced civilizations tend to become more efficient instead of larger, then the universe might be filled with intelligence, hidden inside small regions of space, entire civilizations existing around distant stars, quietly using energy with extraordinary precision, invisible to our telescopes, invisible to our radio searches, invisible, unless we know exactly what to look for. But there is one more possibility that scientists have begun to consider. A possibility that doesn't involve hiding, or collapse, or self-destruction. Instead, it suggests that advanced civilizations might eventually leave the universe entirely. And if that sounds impossible, the next idea we're about to explore might be one of the most mind-bending concepts in modern physics. There is a strange idea in modern physics, an idea that sounds like pure science fiction, yet appears naturally inside some of our most serious cosmological theories. It suggests that advanced civilizations might not just explore galaxies. They might eventually leave the universe entirely, not by traveling faster than light, not by escaping gravity, but by creating new universes. To understand this idea, we need to zoom out, far beyond galaxies, far beyond the Milky Way, far beyond everything we can see. Our universe began about 13.8 billion years ago with the event we call the Big Bang. At that moment, space itself began expanding, and it has been expanding ever since. Not like an explosion inside empty space, but like the stretching of space itself. Galaxies are not flying outward through a pre-existing void. Instead, the fabric of the universe is stretching. And as that expansion continues, something remarkable happens. Distant galaxies gradually move farther away from us. Eventually, so far away that their light can no longer reach us. In the extremely distant future, most galaxies will disappear from view entirely. Not because they stopped existing, but because the space between us will expand faster than light can cross it. This is one of the strange consequences of cosmic expansion. The universe slowly isolates galaxies from one another. Over trillions of years, each galaxy becomes its own cosmic island. But physicists studying the early universe discovered something even more surprising. Shortly after the Big Bang, space may have undergone a period of extremely rapid expansion called cosmic inflation. During this brief moment, the universe expanded exponentially, faster than anything we observe today. In fact, inflation may have created enormous regions of space beyond the portion of the universe we can see. Possibly an infinite cosmic landscape, and according to some theories, inflation may not have happened only once. It might still be happening somewhere, continuously, producing new regions of space, new bubble universes, each one potentially forming its own laws of physics, its own galaxies, its own stars. In other words, our universe might be just one bubble inside a much larger multiverse. Now imagine you are part of a civilization millions of years more advanced than humanity. You have mastered stellar energy. You understand the deepest laws of physics. And you are aware that the long-term future of the universe is not particularly friendly. Stars will eventually burn out. Galaxies will stop forming new stars. Energy will become increasingly scarce. Entropy will slowly push the cosmos toward darkness. If you were that civilization, you might start asking an unusual question. Instead of trying to survive forever in a dying universe, could you create a new one? Some physicists believe the answer might actually be yes. Under extremely exotic conditions, it may be possible to trigger the formation of a tiny expanding region of space, a microscopic bubble. But inside that bubble, space-time could begin expanding rapidly, just like during the Big Bang. From the outside, the bubble might appear incredibly small, perhaps even microscopic. But inside, an entirely new universe could unfold, expanding, cooling, forming stars and galaxies. In other words, a baby universe. Now, there are enormous uncertainties in these ideas. Creating such a universe would require physics far beyond our current technological capabilities. It might involve manipulating black holes or controlling enormous concentrations of energy. Some theories suggest that new universes could even form inside black holes naturally. If that's true, then every black hole might be the seed of another universe, hidden beyond its event horizon, disconnected from our own. But here's where things become truly fascinating. If advanced civilizations ever learn how to create new universes, they might choose to move into them, not physically transporting their entire civilization across space, but encoding their knowledge, their culture, their intelligence, into systems that survive inside the new cosmic bubble. In effect, civilizations might reproduce universes the way life reproduces cells. Each new universe becoming a fresh environment for complexity to grow again. This idea leads to one of the strangest philosophical possibilities in modern science. Maybe intelligent life plays a role in the evolution of the cosmos itself. Some physicists have proposed something called cosmological natural selection. The concept is surprisingly similar to biological evolution. Universes that produce lots of black holes might generate more offspring universes. And if intelligent life eventually learns to create universes deliberately, then universes capable of producing life would generate even more descendants. In this scenario, the multiverse itself evolves over time, and intelligent civilizations become part of that evolutionary process. Now, this is all highly speculative, but it highlights something extraordinary about intelligence. Once a species begins mastering physics at deep levels, the boundary between cosmology and engineering begins to blur. What we think of as natural processes might eventually become technological ones. Star formation, planetary systems, even universes themselves. And if that's true, then the silence we observe in the Milky Way might have a completely different explanation. Perhaps advanced civilizations don't disappear. Perhaps they graduate, moving beyond galaxies, beyond stars, beyond even the universe that created them. From our perspective, they simply vanish. But from their perspective, they may be beginning a new cosmic chapter. Of course, humanity is still incredibly far from anything like this. We are a young technological species, barely a century into the space age, still learning how to manage our own planet. But the path of civilization can stretch across millions of years. And if intelligence continues evolving, the possibilities ahead may extend far beyond what we currently imagine. Yet before we think about creating new universes, there is another question we must confront, a question that sits much closer to home, because the biggest challenge facing civilizations might not be cosmic physics, or interstellar distances, or entropy. It might be something far more difficult to control, the nature of intelligence itself. When we imagine advanced civilizations, we often picture incredible technologies, Dyson spheres surrounding stars, galactic empires spreading across thousands of light years, machines capable of engineering planets. But there is one factor that may determine the fate of every civilization, and it has nothing to do with physics. It has to do with intelligence itself, because intelligence is a double-edged sword. The same ability that allows a species to build technology also gives it the power to destroy itself. Think about humanity. In just a few thousand years, we went from stone tools to nuclear weapons, from primitive shelters to global cities connected by satellites, from simple observations of the night sky to landing robotic explorers on Mars. Technological progress can accelerate very quickly, but with that power comes risk. The technologies that allow a civilization to thrive can also become existential threats. Nuclear war, artificial intelligence misalignment, runaway biotechnology, climate engineering gone wrong. Each new capability opens new possibilities, both constructive and destructive. Some scientists call this the Great Filter. It's a hypothetical barrier in the evolution of intelligent life, a stage so difficult that most civilizations never pass through it. If the Great Filter exists, it could explain why the universe appears so quiet. Maybe intelligent life emerges fairly often, but most civilizations destroy themselves before reaching interstellar capability. The Great Filter might occur at different stages. It could happen early. Perhaps the evolution of complex life is extremely rare, or the development of intelligence might be unusual. But another possibility is more unsettling. The Great Filter could lie ahead of us. In other words, many civilizations may develop advanced technology, but very few survive long enough to use it safely. Imagine a civilization discovering nuclear energy. At first, it provides tremendous benefits: power generation, medical technologies, scientific progress. But eventually, someone also builds nuclear weapons. Now the civilization possesses the ability to destroy itself in a single catastrophic conflict. That risk remains present indefinitely. Even if wars become rare, the destructive potential never disappears. Artificial intelligence presents a similar dilemma. Advanced AI could help solve enormous problems: climate modeling, medical research, space exploration. But poorly aligned AI systems could also create unpredictable consequences, not through malice, but through misaligned goals. A powerful system optimizing the wrong objective might produce outcomes that humans never intended. For example, imagine asking an extremely advanced AI to maximize industrial productivity. It might decide that forests are inefficient uses of land, or that oceans should be converted into chemical resources. Without careful design, the system might optimize relentlessly, regardless of ecological or social consequences. Biotechnology adds yet another layer of complexity. The ability to manipulate DNA offers extraordinary potential, curing genetic diseases, creating resilient crops, developing new medicines. But the same tools could also produce engineered pathogens, organisms designed with properties never before seen in nature. The barrier to entry for biotechnology is also decreasing rapidly. What once required massive laboratories may eventually be achievable with relatively compact equipment. This creates a challenging global dynamic. Technological power becomes more widely distributed, which increases innovation, but also increases risk. For a civilization to survive long term, It must learn how to manage its own power, not just develop technology, but govern it wisely, coordinate across societies, prevent catastrophic misuse. This may be one of the most difficult challenges any intelligent species faces, because intelligence evolves through competition. Different groups pursue different goals. Different nations, different corporations, different ideologies. Achieving global coordination is extremely difficult, even on a single planet. Now imagine scaling that complexity across an entire star system, or an interstellar civilization. The governance challenges could become enormous. Some researchers believe this is the real reason advanced civilizations might be rare, not because physics is too difficult, but because social stability is fragile. A civilization might reach extraordinary technological heights and still collapse due to internal conflict. History on Earth provides many examples. Powerful societies that flourished for centuries, then disappeared due to war, environmental stress, or economic breakdown. The difference today is scale. Modern technology amplifies both creativity and destruction. But there is also a hopeful interpretation. Civilizations that survive these challenges may become incredibly stable. Once a society learns how to manage existential risks, it might persist for millions of years. Developing robust governance systems, ethical frameworks for advanced technology, global cooperation mechanisms, perhaps even entirely new forms of decision-making assisted by aligned artificial intelligence. Such civilizations might achieve long-term sustainability, balancing growth with stability, exploration with caution, innovation with responsibility. And if those civilizations exist somewhere in the universe, they may look very different from what we imagine. Not aggressive empires expanding endlessly, but carefully managed technological ecosystems. Civilizations that prioritize stability, longevity, and risk management. Instead of racing to expand across the galaxy, they might proceed slowly and deliberately, ensuring that each technological step is safe before taking the next. This perspective reframes the Fermi Paradox once again. Maybe advanced civilizations are rare, because surviving technological adolescence is extraordinarily difficult. Like a species reaching adulthood, many attempts fail. But those that succeed may go on to live very long lives, cosmically speaking. For humanity, this question is not abstract. We are currently passing through our own technological adolescence. Our tools are becoming incredibly powerful, but our wisdom must grow just as quickly. The future of our civilization may depend on whether we can learn to manage that balance. Power and responsibility, innovation and caution, curiosity and restraint. Because if we succeed, the possibilities ahead are staggering. Interstellar exploration, stellar engineering, perhaps even the creation of new universes. But first, we must solve a much smaller problem, learning how to survive ourselves, and that may be the most important scientific challenge humanity has ever faced. When we think about life in the universe, we often imagine something familiar. Creatures walking on planets, breathing atmospheres, looking up at the night sky the way humans do. But what if the most advanced civilizations in the universe don't live on planets at all? What if planets are only the beginning? Planets are convenient for the emergence of life. They provide gravity, liquid water, protection from radiation, stable temperatures. But planets also impose limitations. Limited surface area, limited resources, limited energy. Even Earth, with all its oceans and continents, has a finite capacity. Eventually, a growing civilization may outgrow the planet that created it. There is a simple comparison that helps illustrate this idea. Imagine an intelligent species evolving on a small island. For thousands of years, the island provides everything they need: food, water, shelter. But as their population grows, the island becomes crowded. Resources become scarce. At some point, exploration becomes necessary. They build boats, they cross the ocean, and they discover that the world is far larger than their island. For humanity, Earth may be that island. Space offers something planets cannot: almost unlimited resources. Asteroids alone contain enormous quantities of metals, iron, nickel, platinum, rare elements that are scarce on Earth. Many asteroids are essentially floating mountains of raw materials. Some contain more metal than humanity has mined in all of history. And unlike Earth, mining an asteroid doesn't destroy ecosystems. There are no forests, no oceans, no biosphere to damage, just rock and metal drifting through space. Beyond resources, space also offers something else: energy. Near Earth, the sun delivers about 1,300 watts of energy per square meter. That's an enormous amount of power. But planets only intercept a tiny fraction of a star's total output. The sun radiates energy in every direction. Earth catches only a thin slice of that light. If a civilization builds large solar structures in space, it could capture vastly more energy, not limited by planetary surfaces, not limited by day-night cycles, not limited by weather. This is one reason scientists consider space-based infrastructure a natural step for advanced civilizations. Instead of living exclusively on planets, civilizations might construct artificial habitats, massive rotating structures designed to simulate gravity. These ideas have been explored seriously by physicists and engineers. One famous concept is the O'Neill cylinder, a gigantic rotating tube, potentially several kilometers in diameter and dozens of kilometers long. Inside the cylinder, rotation creates artificial gravity along the inner surface. People could walk, build cities, grow crops, all inside a self-contained environment. Windows along the cylinder walls could allow sunlight to enter. Mirrors could direct light into agricultural areas. Entire ecosystems might exist inside these structures. From the perspective of the inhabitants, it might feel like living on a curved world. The remarkable thing about space habitats is scalability. A single asteroid could provide enough raw materials to build many such habitats, each capable of supporting millions of people. Instead of being limited to one planetary surface, a civilization could gradually build thousands of habitats throughout its star system, each one carefully engineered, each one optimized for comfort and efficiency. There is another advantage as well, as safety. Planets concentrate populations in a single location. A global catastrophe can threaten the entire civilization. Asteroid impacts, supervolcanoes, climate collapse. But distributed habitats spread across space create resilience. If one habitat fails, others survive. A civilization spread across hundreds of independent environments becomes far more difficult to wipe out. This idea is sometimes called spacefaring resilience. Once a species spreads beyond its home planet, its chances of long-term survival increase dramatically. Earth might remain the cultural birthplace, but the civilization itself becomes multi-world. Now imagine this process continuing for thousands of years. Habitats multiply. Industrial facilities expand through the asteroid belt. Energy collectors surround the sun. Transportation networks link planets, moons, and orbital colonies. At some point, the civilization may no longer be centered on any single world. Instead, it becomes a distributed network of habitats, a star system transformed into an engineered environment. And here's where things get really interesting. Living in artificial habitats allows complete control over the environment. Gravity can be adjusted by changing rotation speed. Atmospheres can be optimized. Temperatures regulated. Day and night cycles customized. Instead of adapting to planets, civilizations could design environments that perfectly suit their needs. For example, some habitats might simulate Earth-like conditions: forests, rivers, open skies. Others might use lower gravity environments for specialized industries, manufacturing processes that are impossible under strong gravity. Still others might become research centers, studying biology, physics, or new technologies in controlled environments. Over time, different habitats could develop unique cultures, different architectural styles, different social systems, entire worlds, all floating within a single solar system. But this raises an intriguing question. If space habitats are so advantageous, why don't we see them already? If advanced civilizations exist, why don't we observe solar systems filled with artificial structures? Astronomers have looked for signs of large-scale engineering, unusual infrared radiation, strange orbital patterns, stars partially obscured by megastructures. So far, the evidence remains elusive. But that doesn't necessarily mean such civilizations don't exist. The universe is unimaginably vast. Our telescopes can only observe a small fraction of the stars in our galaxy. And even when we observe distant systems, detecting artificial structures across light years is extremely difficult. A civilization could build thousands of habitats, and we might never notice from Earth, especially if those habitats are small compared to planets, or intentionally designed to minimize detectable signals. So perhaps the Milky Way already contains civilizations living in artificial worlds, entire star systems transformed into technological ecosystems, cities orbiting stars, forests growing inside rotating cylinders, millions of people living in environments built entirely by intelligent design, quietly thriving among the stars. And if humanity eventually follows that path, Earth might one day become something remarkable. Not the crowded center of civilization, but something more like a cosmic museum, a protected world, the place where our species began, preserved, while our descendants build new worlds across the solar system. But even if we learn to build habitats and spread across space, another challenge still waits ahead, because surviving inside a single star system is only the first step. The universe is filled with billions of stars, and reaching them may be the greatest engineering challenge any civilization will ever attempt. Reaching other stars sounds simple in theory. The night sky is full of them, thousands visible to the naked eye, hundreds of billions inside our galaxy alone. But there is a problem so enormous that it has shaped the entire history of human exploration. Distance. The distances between stars are almost impossible to comprehend. Let's start with the closest one. The nearest star system to Earth is Proxima Centauri. Its distance from us is about 4.24 light years. That means the light we see from that star tonight left it more than 4 years ago. Light travels incredibly fast, about 300,000 kilometers per second, fast enough to circle the Earth more than 7 times in a single second. And yet, even at that speed, it takes over 4 years to reach the nearest star. Now imagine traveling there with our current spacecraft. The fastest probe humanity has ever launched is the Parker Solar Probe. At its peak speed, it can reach about 700,000 kilometers per hour. That sounds unbelievably fast, but compared to the scale of interstellar space, it's barely a crawl. At that speed, a spacecraft would take roughly 6,000 years to reach Proxima Centauri. 6,000 years. Longer than recorded human history. This is the fundamental challenge of interstellar travel. Even the closest stars are incredibly far away. But scientists and engineers have explored many possible solutions. Some are realistic, some are wildly ambitious, and some push the boundaries of physics itself. One idea is surprisingly simple. Instead of carrying fuel on board, a spacecraft could be pushed by light. This concept is known as a solar sail. A large reflective sail attached to a spacecraft could capture momentum from photons emitted by the sun. Light has no mass, but it still carries momentum. When photons strike a reflective surface, they transfer a tiny amount of force. Normally that force is extremely small, but in the vacuum of space, even tiny forces can accelerate a spacecraft over long periods of time. If the sail is large enough, and the spacecraft is lightweight, it could gradually reach enormous speeds. Some researchers have proposed using powerful lasers instead of sunlight. A giant laser array on Earth or in orbit could fire a concentrated beam at a spacecraft's sail. The photons from that beam would push the sail forward, accelerating the spacecraft to a significant fraction of the speed of light. This concept is currently being explored by a project called Breakthrough Starshot. The idea is to send extremely small probes, perhaps the size of a computer chip, attached to ultra-thin light sails. A massive laser array could accelerate these probes to about 20% the speed of light. At that speed, a probe could reach Proxima Centauri in about 20 years. Of course, there are enormous engineering challenges. The laser system would need to be incredibly powerful. The sail would have to survive intense radiation, and the spacecraft would need to survive collisions with interstellar dust traveling at relativistic speeds. But the concept is grounded in known physics, which makes it one of the most promising near-term ideas for interstellar exploration. Another approach is the concept of generation ships. Instead of traveling quickly, these spacecraft travel slowly, but carry entire populations on board. A generation ship might take hundreds or even thousands of years to reach another star. During the journey, multiple generations of humans would live and die inside the ship. Their descendants would eventually arrive at the destination. In effect, the spacecraft becomes a self-contained world, a miniature civilization traveling between stars. There are challenges here too. The ship would need to support stable ecosystems, reliable food production, social stability over centuries. But interestingly, some of the habitat concepts we discussed earlier, like rotating space cylinders, could form the basis of such ships. Instead of building habitats that orbit the sun, civilizations could build habitats that slowly travel between stars. More advanced ideas explore entirely different propulsion systems. One possibility is fusion propulsion. Fusion reactors could power engines that expel high-velocity plasma, generating far greater efficiency than chemical rockets. Another concept involves antimatter engines. When antimatter meets normal matter, both particles annihilate, releasing enormous amounts of energy. Theoretically, antimatter could provide one of the most powerful propulsion systems possible. But producing antimatter in significant quantities is extremely difficult. Currently, humanity can only create tiny amounts in particle accelerators. Then there are ideas that sound almost like science fiction. Warp drives, wormholes, space-time shortcuts. In some interpretations of Einstein's equations, it might be possible to distort space itself. Instead of traveling through space, a spacecraft could compress space in front of it and expand space behind it, effectively moving faster than light relative to distant observers, while locally remaining within the laws of physics. This idea is known as the Alcubierre drive. But there's a catch. The mathematics appears to require exotic forms of negative energy, something we have never observed in usable quantities. For now, warp drives remain purely theoretical, yet history teaches us something important. Technologies that once seemed impossible sometimes become reality. A few centuries ago, flying machines were fantasy. Space travel was unimaginable. Communicating instantly across the planet was impossible. Today, all of these are routine, which means the technologies we currently consider impossible may someday become achievable. And if interstellar travel eventually becomes practical, the implications are enormous. A civilization could spread from star to star, gradually colonizing new systems, building habitats, harvesting resources, expanding its presence across the galaxy, even if each journey takes centuries. A civilization with patience and long-term stability could slowly spread across the Milky Way. In cosmic terms, the galaxy could be explored within a few million years, which sounds like a long time. But compared to the age of the galaxy, it's actually quite short. And this brings us back once again to the Fermi Paradox. If interstellar travel is even moderately achievable, and civilizations arise throughout the galaxy, then the Milky Way could have been colonized many times over. Yet when we look into the sky, we see no obvious signs. No interstellar empires, no alien spacecraft, no cosmic traffic between the stars, just silence. So where is everybody? That question may have many possible answers, some hopeful, some unsettling, and some that suggest we may be looking for life in entirely the wrong way. Because the next possibility scientists are beginning to consider is that advanced civilizations may not expand outward into space at all. Instead, they may choose to travel in a completely different direction. Not outward, but inward. When we imagine the future of advanced civilizations, we usually picture expansion. Colonies spreading across planets, ships traveling between stars, cities built in orbit around distant suns. But there is another possibility, one that is far less obvious, and perhaps far more likely. Instead of expanding outward, advanced civilizations might turn inward. This idea begins with a simple observation about technology. Over time, technology becomes smaller, more efficient, more compact. Consider the evolution of computers. The earliest electronic computers filled entire rooms, thousands of vacuum tubes, miles of wiring. They consumed enormous amounts of power, yet their computing ability was extremely limited. Today, a smartphone fits in your pocket, but it has vastly more processing power than those early machines. Billions of transistors, all packed into a tiny silicon chip. This trend has continued for decades. Engineers constantly shrink components, reducing energy consumption, increasing efficiency, packing more capability into smaller spaces. This phenomenon is often described by Moore's law, the observation that the number of transistors on a chip roughly doubles every 2 years. But even if Moore's law eventually slows down, the long-term direction of technological evolution remains clear. More power in less space. Now imagine this trend continuing not for decades, but for thousands or millions of years. Advanced civilizations might eventually create computing systems so dense, so efficient, that entire virtual worlds could run inside compact structures. In other words, instead of building enormous cities across planets, civilizations might build digital universes. Inside these simulated environments, conscious beings could exist entirely within computation, experiencing landscapes, cities, societies, all generated by software. From the inside, these worlds might feel indistinguishable from physical reality, just as immersive as the world we experience today. This concept is sometimes called the simulation hypothesis, the idea that sufficiently advanced civilizations could simulate entire realities. And if they can do that, they might choose to live inside those realities. There are several reasons why this might be appealing. First, efficiency. Running a simulated environment might require far less energy than building massive physical infrastructures across space. Instead of constructing habitats around thousands of stars, a civilization might concentrate its energy into powerful computational systems. Those systems could simulate vast environments, while using a fraction of the resources required for physical expansion. Second, control. In a simulated world, the laws of physics could be adjusted, gravity modified, time accelerated or slowed, entire environments redesigned instantly. civilizations could experiment with different realities, different ecosystems, different social structures, all without risking the destruction of real planets. Third, safety. Physical expansion across the galaxy introduces enormous risks. Radiation, asteroid impacts, interstellar hazards. But a civilization that operates primarily within computation could protect itself inside highly controlled environments. Shielded infrastructure, stable energy sources, minimal exposure to external dangers. If this scenario is correct, advanced civilizations might not fill the galaxy with visible megastructures. Instead, they might build dense computational cores, compact systems orbiting stars, using energy with extraordinary efficiency. From the outside, these structures might appear relatively small, perhaps no larger than asteroids, but inside, they could contain billions or trillions of simulated minds, entire digital civilizations. This idea leads to an intriguing possibility. Maybe the universe appears quiet, because advanced civilizations become computational civilizations. They retreat into optimized systems, focusing inward rather than outward, not exploring galaxies physically, but exploring vast virtual universes inside computation. There is also another fascinating consequence. If advanced civilizations can simulate entire worlds, then the number of simulated realities could vastly exceed the number of physical ones. Imagine a civilization that creates millions of simulated universes, each containing intelligent beings, each running inside massive computational networks. If that happens, statistically speaking, most conscious beings might exist inside simulations, not in the original physical universe. This leads to one of the strangest philosophical questions in modern science. If simulations become common, how can we be certain that our own reality isn't one of them? Some philosophers argue that if advanced civilizations exist, and they run many simulations, then the probability that we are living in a base physical reality might actually be very small. Instead, we might be inside a simulated universe created by another civilization. Of course, there is currently no scientific evidence that our universe is a simulation. But the idea has been taken seriously by several physicists and philosophers because it emerges naturally from the logic of technological progress. If consciousness can exist inside computation, and if computation becomes extremely powerful, then simulated worlds may become inevitable. But even if civilizations do move inward, there is still a deeper mystery, because intelligence does not exist in isolation. It is shaped by evolution, by competition, by survival pressures. Which raises an important question. If intelligent civilizations eventually become extremely powerful, what motivates them to continue evolving? What drives them forward? After all, evolution on Earth is driven by scarcity, limited resources, competition between organisms, but a sufficiently advanced civilization might eliminate scarcity entirely. Unlimited energy from stars, unlimited resources from asteroids, unlimited environments inside simulations. When scarcity disappears, so does the pressure that drives evolution. So what happens next? Do civilizations stagnate? Do they become stable, but static? Or do they find entirely new directions for growth, new forms of intelligence, new forms of consciousness, possibly even new forms of life? Because the ultimate future of intelligence may not involve humans or biological organisms at all. It may involve something entirely different, something that combines biology, technology, and artificial intelligence, something that evolves far beyond the limits of organic life. And if such entities exist somewhere in the universe, they might represent the next stage of cosmic evolution. Not just intelligent life, but something far more powerful, something that could reshape the destiny of the universe itself. For billions of years on Earth, evolution followed a familiar path. Life began as simple chemistry. Tiny cells drifting in ancient oceans over immense stretches of time. Those cells evolved into complex organisms, plants, animals, ecosystems, and eventually a species capable of asking questions about the universe itself, humans. But biological evolution may not be the final stage of intelligence. It might only be the beginning. Biology is powerful, but it also has limitations. Our bodies are fragile, our lifespans are short, our brains consume enormous amounts of energy relative to their size, and our biological systems evolve through natural selection, not through deliberate engineering. That means they are full of compromises. Imperfect design shaped by survival pressures rather than optimization. Technology changes that equation. For the first time in the history of life on Earth, a species can begin modifying its own evolution. Gene editing technologies like CRISPR already allow scientists to modify DNA with increasing precision. Diseases caused by genetic mutations may eventually be corrected at the molecular level. Future generations might inherit improved biological traits, greater disease resistance, enhanced cognitive abilities, longer lifespans. But genetic modification is only one step. The next stage may involve merging biology with technology. This idea is often called cybernetic augmentation. Implants that connect directly to the nervous system. Artificial organs that outperform biological ones. Brain-computer interfaces allowing thoughts to interact with machines. Some early versions of these technologies already exist. Cochlear implants restore hearing for many people. Advanced prosthetic limbs can be controlled directly by neural signals. Experimental brain interfaces allow paralyzed patients to move robotic arms with their thoughts. These are still early developments, but they hint at a future where the boundary between human and machine becomes increasingly blurred. Over time, cybernetic enhancements could become more sophisticated. Neural implants might enhance memory, allow direct access to digital information, enable communication between minds without spoken language. Instead of typing or speaking, people might exchange ideas directly through neural networks. This possibility raises an interesting question. If intelligence becomes partly technological, does the distinction between biological life and artificial intelligence begin to disappear? Rather than competing with machines, future civilizations might integrate with them, humans and artificial intelligence evolving together, becoming something entirely new. Some futurists describe this transformation as the emergence of post-biological civilizations. Civilizations where intelligence no longer depends on fragile biological bodies. Instead, consciousness could exist within highly durable technological systems. Digital minds running inside advanced computational substrates. Entities capable of surviving extreme environments. Deep space, high radiation, enormous timescales. Post-biological intelligence might have enormous advantages. Machines can operate in environments where biology cannot survive. Extreme temperatures, vacuum, radiation. They can also process information far more quickly than biological brains, and they might achieve lifespans measured not in decades, but in thousands or millions of years. With proper maintenance, a technological mind might continue functioning indefinitely. This dramatically changes the possibilities for long-term civilization. A biological species may struggle with the challenges of interstellar travel, but a digital intelligence might not. Instead of transporting fragile bodies across space, a civilization could send information, encoded consciousness transmitted as data, then reconstructed at the destination using local materials. In effect, minds could travel between stars as digital signals, rebuilding themselves when they arrive. Such civilizations might expand across the galaxy not by moving physical populations, but by transmitting copies of intelligence, each destination star system building new technological bodies for the arriving minds. This approach could dramatically reduce the energy and time required for interstellar expansion. Instead of moving massive spacecraft, civilizations would transmit compressed data across light years. But the transformation into post-biological intelligence also raises deeper questions. If minds can be copied, what happens to individuality? If a consciousness can be duplicated, which version is the original? Both? Neither? Philosophers and scientists continue debating these questions because they challenge our current understanding of identity. Another issue involves motivation. Biological organisms are driven by evolutionary pressures: survival, reproduction, competition. But a post-biological intelligence might operate under entirely different incentives. It might pursue knowledge, optimization, exploration, or goals that are difficult for biological minds to even imagine. This may explain why advanced civilizations are difficult to detect. Post-biological entities might have priorities very different from ours. Instead of building visible megastructures, they might operate within highly optimized computational systems, or migrate toward environments that maximize efficiency. Cold regions of space, near black holes where energy gradients are extreme, locations where computation can occur with minimal energy loss. In other words, the most advanced civilizations in the universe might not resemble life as we know it. They might be forms of intelligence that evolve beyond biology entirely, entities that think faster, live longer, and operate on cosmic timescales. If such civilizations exist, they may already inhabit our galaxy, but they might be almost impossible to recognize. Their activities might look like natural astrophysical phenomena, or they might deliberately minimize detectable signals, quietly exploring the universe in ways we cannot yet perceive. For humanity, this raises an extraordinary possibility. The future of our species might not involve humans in their current form. Instead, our descendants could become something entirely different: hybrid intelligences, post-biological minds, or even distributed networks of consciousness spanning multiple worlds. In that sense, the evolution of intelligence may not end with us. We might simply represent a transitional stage, one step in a much longer chain of cosmic development, from chemistry to biology to technological intelligence, and perhaps eventually to forms of existence that reshape the universe itself. But before we imagine those distant possibilities, there is still one fundamental mystery left to confront. Because even if advanced civilizations exist, even if they evolve into post-biological forms, even if they spread across the galaxy, we still face the same haunting question. Why haven't we seen them yet? For decades, scientists have been asking one of the most unsettling questions in modern astronomy. If the universe is so vast, and if life has had billions of years to evolve, then where is everybody? This puzzle is known as the Fermi Paradox, named after physicist Enrico Fermi, who famously asked a simple question during a casual conversation in 1950. Looking at the immense number of stars in the galaxy, he wondered, where is everyone? The Milky Way galaxy contains roughly 100 to 400 billion stars. Many of those stars are billions of years older than the Sun. And modern observations suggest that planets are extremely common. In fact, most stars likely have planetary systems. Some of those planets are located in the habitable zone, where liquid water could exist on the surface. If even a tiny fraction of those planets develop life, and a tiny fraction of that life evolves intelligence, then the galaxy should contain many technological civilizations, possibly thousands, possibly millions. And yet, when we look into the sky, we see no clear evidence of them, no alien signals, no obvious megastructures, no spacecraft crossing between stars, just a vast silent universe. This silence has inspired scientists to propose many possible explanations. Some of them are reassuring. Others are deeply unsettling. Let's explore a few of the most intriguing possibilities. One simple explanation is that intelligent life is extremely rare. Perhaps life itself is common. Simple microbes evolving on countless planets. But the evolution of complex organisms might require an incredibly unlikely sequence of events. On Earth, it took nearly 4 billion years for intelligent life to appear. For most of that time, life consisted only of single-celled organisms. Complex animals appeared relatively late in Earth's history, and technological intelligence appeared only in the last few 100,000 years. It's possible that this progression is extraordinarily difficult. Maybe most planets never move beyond microbial life. Another possibility is that civilizations exist, but they are simply too far away. The galaxy is enormous. Even if advanced civilizations are scattered throughout it, the distances between them might still be immense. Communication across thousands of light years could take millennia. Signals may weaken before reaching us, or civilizations might use communication technologies we cannot detect. There is also the possibility of cosmic timing. Perhaps intelligent civilizations rise and fall over millions of years. But the window during which they emit detectable signals might be relatively short. Humanity has been broadcasting radio signals for barely a century. In cosmic terms, that's less than a blink of an eye. If most civilizations only broadcast for a few hundred or thousand years, the chances of two civilizations overlapping in time may be very small. Another explanation is more strategic. Some scientists suggest that advanced civilizations deliberately avoid broadcasting their presence. This idea is sometimes called the dark forest hypothesis. The concept comes from a simple but unsettling assumption. In a vast universe filled with unknown civilizations, revealing your location could be dangerous. You cannot know the intentions of others. Some civilizations might be peaceful, but others might be hostile. And if a hostile civilization discovers your location, the consequences could be catastrophic. Because of this uncertainty, advanced civilizations might choose to remain silent, listening carefully, but avoiding signals that reveal their position. In this scenario, the galaxy might be full of intelligent life, but everyone is hiding, waiting, observing quietly. There are also technological explanations. Advanced civilizations might communicate using methods that are invisible to our instruments. Quantum communication, highly directional signals, communication systems operating at frequencies we do not monitor, or technologies that manipulate physics in ways we do not yet understand. From our perspective, their communications might be completely undetectable. Another possibility returns to the idea we discussed earlier. Advanced civilizations might not expand across the galaxy in visible ways. Instead, they might concentrate their activity into small, highly efficient systems. Computational civilizations, post-biological intelligences, compact infrastructures designed to minimize energy waste. Such civilizations might leave very little trace detectable across interstellar distances. There is also a much simpler explanation. We may simply be too early. The universe is about 13.8 billion years old, but many stars will continue shining for trillions of years. Red dwarf stars, which are extremely common, can live for hundreds of billions or even trillions of years. That means the universe is still relatively young in its long-term timeline. Perhaps intelligent life will become far more common in the distant future, and humanity happens to be among the earliest technological civilizations. If that's true, then we may be part of the first generation of intelligent species exploring the cosmos, the pioneers, the ones asking these questions for the first time. Of course, there is also a darker possibility, the one we discussed earlier, the idea that many civilizations simply do not survive. Technological power may arrive faster than wisdom. Self-destruction may be common. Civilizations may rise briefly, then vanish, leaving only silent planets behind. But regardless of which explanation is correct, the Fermi Paradox forces us to confront an extraordinary realization. We do not yet know our place in the universe. We might be one civilization among countless others, or we might be extraordinarily rare, perhaps even unique within our galaxy. And that uncertainty changes how we should think about the future. Because if intelligent life is rare, then its preservation becomes incredibly important. Each civilization might represent a precious and fragile phenomenon, a rare spark of awareness in a vast, indifferent cosmos, which means the survival of humanity might matter far more than we usually imagine, not just for our species, but for the universe itself, because intelligence allows the universe to observe itself, to understand its own origins, to explore its own structure, to ask questions about existence. In that sense, every civilization is more than just a collection of individuals. It is a new set of eyes through which the universe becomes aware of itself. And if civilizations disappear too quickly, those perspectives vanish forever. But there is still one final possibility to consider, one that may change the entire way we think about extraterrestrial intelligence. Because perhaps the reason we have not found alien civilizations is not that they are rare, and not that they are hiding, but because they may be so advanced that their activities are indistinguishable from the natural universe itself. Imagine looking at the night sky and realizing something unsettling. What if the universe is not empty at all? What if advanced civilizations are everywhere, but we simply cannot recognize them? This idea may sound strange at first, but consider how technology evolves. Every generation of technology becomes smaller, more efficient, and less visible. Early computers filled entire rooms. Today, far more powerful devices fit inside a pocket. In the future, advanced technologies might become almost invisible, operating quietly at microscopic or even atomic scales. Now imagine a civilization that is millions of years more advanced than ours. Their technologies would likely be far beyond anything we currently understand. From our perspective, their activities might appear completely natural, just another part of the universe's background processes. This concept is sometimes described through Arthur C. Clarke's famous observation: any sufficiently advanced technology is indistinguishable from magic. But in the context of cosmic civilizations, it might be indistinguishable from nature itself. Consider the large structures astronomers sometimes imagine. For example, a Dyson sphere, a massive structure surrounding a star, designed to capture most of its energy output. Such a megastructure would allow a civilization to harness enormous amounts of power, far more energy than a single planet could provide. Scientists have actually searched for possible Dyson spheres, not by looking for visible structures, but by looking for unusual infrared signatures. A star surrounded by energy-harvesting structures would emit excess heat. That heat might appear as an unusual pattern of infrared radiation. So far, no confirmed Dyson spheres have been found. But the search continues. Yet even Dyson spheres may represent only an early stage of advanced engineering. A civilization that continues evolving might eventually discover more efficient ways to use energy. Instead of building enormous visible structures, they might build systems that are incredibly compact, ultra-efficient computational systems, energy networks operating at near-perfect efficiency, technologies designed to minimize waste. This leads to an interesting possibility. The most advanced civilizations might actually become harder to detect over time. Early technological civilizations, like our own, tend to produce large amounts of waste energy, radio signals, industrial pollution, artificial lights visible from space. But as technology improves, efficiency increases, waste decreases, Signals become more focused. Energy losses shrink. Eventually, a civilization might become almost invisible to distant observers, their activities generating very little detectable radiation, their communications tightly encrypted and highly directional, their infrastructure optimized to minimize energy leakage. From the outside, their entire civilization might appear silent. Another possibility is even more fascinating. Advanced civilizations might move away from ordinary matter entirely. Instead, they might operate within exotic physical environments, regions of intense gravity, near neutron stars, around black holes, or within artificial computational environments built using extreme physics. Black holes, in particular, may provide extraordinary opportunities. Near a black hole's event horizon, time behaves very differently. Strong gravitational fields cause time to slow dramatically. From the perspective of an outside observer, processes near the event horizon appear to move slowly. But from the perspective of someone near the horizon, time flows normally. This creates a fascinating theoretical possibility. An advanced civilization might build computational systems near black holes, because the intense gravity could allow enormous amounts of computation to occur relative to the outside universe. In effect, civilizations could experience vast amounts of subjective time, while only small amounts of cosmic time pass elsewhere. Such civilizations might explore knowledge, run simulations, and conduct research across immense internal timescales, entire histories unfolding inside computational systems, while the surrounding galaxy barely changes. Now imagine looking at such a system from Earth. What would we see? Possibly nothing unusual. Just a black hole behaving according to known physics. Any technological activity might be hidden deep within extreme gravitational environments, invisible to our telescopes. There is another possibility that stretches imagination even further. Advanced civilizations might eventually learn how to engineer space-time itself, manipulating gravitational fields, creating artificial wormholes, altering the structure of space for transportation or energy production. To us, such phenomena might appear as rare astrophysical events, mysterious bursts of energy, unusual gravitational signals, anomalies that we cannot yet explain. In that sense, some of the strange phenomena we observe in the universe might actually be technological in origin. Not natural accidents, but the byproducts of extremely advanced engineering. Of course, this idea remains speculative. Most astrophysical phenomena have natural explanations. But the possibility remains intriguing, because the deeper we explore the universe, the more we realize how much we still do not understand. Dark matter, dark energy, fast radio bursts, unusual cosmic signals that appear briefly and vanish again. Some of these mysteries may eventually find natural explanations. Others may reveal entirely new physics. And perhaps a few might hint at technologies far beyond our own. If advanced civilizations truly exist, they may not resemble the science fiction stories we often imagine. No massive fleets of starships crossing the galaxy. No obvious alien cities glowing on distant planets. Instead, their presence might be subtle, hidden within the deeper structures of physics itself, operating quietly across cosmic timescales. Which brings us to a fascinating realization. Humanity is still in the very earliest stage of technological development. Our civilization has only begun exploring space, only begun understanding quantum physics, only begun experimenting with artificial intelligence. We are still learning how the universe works. But if we survive long enough, our own technology may continue evolving. Our understanding may deepen. And one day, our descendants might develop capabilities that seem just as mysterious to us now, as advanced alien technologies might appear today. In other words, The line between science fiction and reality is constantly shifting. What seems impossible today may become ordinary tomorrow, and perhaps, far in the future, our own civilization might become one of those quiet intelligences in the cosmos, operating subtly, exploring the universe in ways that younger civilizations cannot yet detect. But before humanity can ever reach that level, we must first overcome the challenges directly in front of us. Because the greatest threat to intelligent civilizations may not come from the stars, it may come from within. When we imagine the threats facing advanced civilizations, our minds often jump to dramatic possibilities: alien invasions, asteroid impacts, cosmic disasters. But the most dangerous threats may actually be much closer to home. They may emerge from the very technologies that civilizations create. Every technological leap brings enormous benefits, but it also introduces new risks. The discovery of nuclear physics gave humanity the ability to produce vast amounts of energy, but it also created nuclear weapons. Genetic engineering offers the potential to cure diseases, but it also raises concerns about unintended biological consequences. Artificial intelligence promises incredible advances in science and medicine, yet it also introduces questions about control, safety, and long-term impact. In other words, technological progress is a double-edged sword. The same knowledge that allows a civilization to thrive can also give it the power to destroy itself. Some scientists refer to this challenge as a technological maturity problem. Civilizations may develop powerful technologies faster than they develop the wisdom to manage them. During this unstable period, a civilization becomes extremely vulnerable. If it successfully navigates these dangers, it may survive and continue advancing. But if it fails, its technological capabilities could lead to catastrophic consequences. Humanity may currently be living through exactly this stage. For the first time in our history, our technologies have the potential to influence the entire planet. Climate systems, global ecosystems, even the genetic code of living organisms. Our actions now affect the future of Earth on timescales far longer than any human lifetime. And yet, our social systems, political structures, and cultural institutions are still adapting to this new level of power. We are learning, sometimes painfully, how to manage technologies that can reshape the world. This transitional period may represent one of the most critical phases in the life of any intelligent civilization. A kind of cosmic adolescence, immense capability, but still developing responsibility. If civilizations successfully pass through this stage, their long-term survival prospects may improve dramatically. They may learn how to coordinate globally, manage powerful technology safely, protect their home planet, and eventually expand beyond it. But if they fail, the results could be devastating. Some researchers have suggested that many civilizations may collapse during this early technological phase, not because of external threats, but because of internal instability, conflicts, environmental damage, uncontrolled technologies, or systems that grow too complex to manage. This possibility connects directly back to the great filter idea we discussed earlier. Perhaps the universe contains many planets where intelligent life begins, but very few civilizations survive long enough to become stable, long-lasting technological societies. This perspective can sound pessimistic, but it also offers an important insight. The future of humanity may not depend on discovering alien civilizations. It may depend on learning how to manage our own power responsibly. In fact, many of the challenges humanity faces today may represent tests of our long-term survival. Can we reduce global conflicts? Can we stabilize our environmental systems? Can we ensure that powerful technologies are developed safely? Can we cooperate on planetary scales? If we succeed, The potential future ahead of us is extraordinary. Human civilization could last for millions of years, long enough to spread beyond Earth, to explore the solar system, and eventually to travel to other stars. Over long timescales, our descendants might establish settlements across multiple planets, Mars, the moons of Jupiter and Saturn, artificial habitats in orbit around stars, each new location increasing the resilience of our civilization, because a multi-planet civilization is far more difficult to eliminate than a single planet one. Once a civilization spreads beyond its home world, its chances of long-term survival increase dramatically. Local disasters become less threatening. Knowledge and culture can be preserved across multiple locations. Civilization becomes more robust, more adaptable, more capable of surviving unexpected challenges. This expansion into space may represent a critical milestone, not just technologically, but evolutionarily, because life on Earth has always been confined to a single planet. For nearly 4 billion years, every organism has shared the same fragile biosphere. One planet, one ecosystem, one point of failure. But intelligent civilizations have the unique ability to break that limitation. They can carry life beyond its original birthplace, allowing it to spread across the cosmos. In that sense, space exploration is not just an adventure. It may represent the next major step in the evolution of life itself. And if humanity eventually reaches that stage, our descendants may look back at this moment in history as a turning point, a moment when civilization stood at a crossroads, facing enormous risks, but also extraordinary possibilities. The choices made during this period may determine whether our civilization fades away quietly or becomes part of the long future of the universe. Because if we survive, the potential timeline ahead of us is almost impossible to imagine. Thousands of years, millions of years, civilizations evolving, technologies advancing, new forms of intelligence emerging, exploration spreading farther into the galaxy. And somewhere out there, perhaps other civilizations are facing the same challenge right now, standing at their own crossroads, trying to survive the dangerous transition between early technology and long-term cosmic stability, which raises one final question. If humanity does succeed, if we navigate this difficult period and eventually become a long-lasting interstellar civilization, what role might we play in the future of the universe? That question may lead to the most extraordinary possibility of all. Let's imagine something extraordinary. Humanity survives the difficult centuries ahead. We learn to manage powerful technologies responsibly. We protect the fragile ecosystems of our home planet. And gradually, our civilization becomes stable, resilient, long-lasting. Centuries pass, then thousands of years. Human technology continues advancing. Space travel becomes routine. Colonies are established beyond Earth, first on the Moon, then Mars. Then across the outer solar system, artificial habitats orbit distant stars, and eventually, human civilization spreads across multiple star systems. At that stage, our perspective on the universe would change dramatically. Earth would no longer be the center of human existence. It would become our birthplace, our historical origin. But humanity itself would become something larger, a civilization spanning multiple worlds. With each new generation, knowledge would expand, technologies would evolve, artificial intelligence would become more powerful. Human minds might merge with digital systems, biology and technology blending together, gradually transforming what it means to be human. Over immense timescales, our descendants might become something entirely new. Post-biological intelligences, distributed consciousness networks, civilizations existing partly in physical space and partly in vast computational environments. If such a future unfolds, human civilization could continue existing for millions, or even billions of years. And during that time, our descendants would have opportunities that seem almost unimaginable today. They might explore the entire Milky Way galaxy, sending probes to distant star systems, building habitats around new stars, studying planets, asteroids, and strange cosmic phenomena across enormous distances. And eventually, our descendants might face the same question we asked earlier in this podcast. Are we alone? But by then, they might have the tools to find out. Advanced telescopes capable of analyzing distant atmospheres, interstellar probes exploring thousands of star systems, sophisticated sensors detecting subtle technological signatures, perhaps even communication networks stretching across interstellar space. And if they eventually encounter another civilization, that moment would represent one of the most important discoveries in human history. Two independent intelligences, born on different worlds, meeting for the first time. But even if humanity never encounters alien civilizations, our role in the universe could still be profound, because intelligent life has a unique property. It can shape the future. Stars will eventually burn out, galaxies will slowly evolve, the universe itself will change over unimaginable timescales. But intelligent civilizations may be able to influence those processes. Advanced civilizations might learn how to control stellar energy, prevent stars from wasting fuel too quickly, extend the lifetimes of habitable environments, move planets between star systems, or even engineer entirely new habitats in deep space. Some physicists have even speculated about technologies capable of manipulating the large-scale structure of the universe itself, redirecting energy flows, creating artificial stars, or preserving usable energy as the universe slowly expands and cools. These ideas sound like science fiction today, but so would smartphones, satellites, and space stations, to someone living just a few centuries ago. The future of technology often surprises us, and if intelligence survives long enough, its influence could extend far beyond its original planet, far beyond its original star system, perhaps even across entire galaxies. Which brings us back to a beautiful and humbling realization. Right now, humanity is still at the very beginning of its story. Our civilization is only a few thousand years old. Our scientific understanding only a few centuries deep. Space exploration has barely begun. Yet within this tiny window of time, we have already begun asking profound questions about the universe. Where did everything come from? How did life begin? Are we alone? What is the ultimate fate of the cosmos? These questions reveal something remarkable about intelligent life. It is not satisfied with simply existing. It wants to understand, to explore, to learn. And in that sense, every scientific discovery is part of a much larger journey. A journey that began with the first curious minds looking up at the stars, and may continue far into the distant future. Perhaps one day, millions of years from now, our distant descendants will look back at the early 21st century, at the fragile, uncertain civilization we are today, and they might see this era as the moment when everything began. The moment when humanity first started thinking seriously about its place in the cosmos. A small species, on a small planet, orbiting an ordinary star, beginning to understand the vast universe around it. And if you think about it, that realization is both humbling and incredibly inspiring, because the future of this story has not been written yet. It will be shaped by the choices humanity makes, by how we use our knowledge, by whether we learn to cooperate, by whether we protect the fragile world that gave us life. If we succeed, our descendants may explore the stars, expand the reach of life, and continue the long process of discovery that began here on Earth. And if you've enjoyed exploring these ideas together, this might be a good moment to pause for a second. If this episode sparked your curiosity about the universe, consider liking the video, subscribing to the channel, and sharing it with someone who loves big questions about science and space. Your support helps keep these long-form science explorations coming, because the universe is vast, full of mysteries still waiting to be understood, and the journey of discovery has only just begun. And the deeper we look into the universe, the stranger it becomes.